So we're going to be looking at a number of different types of reactions in this class, but in order to understand what's happening during a reaction, we have to actually look at the change in enthalpy, or the change in energy that occurs with these reactions. So here's a potential energy diagram right here, all right? And if you notice, the graph on the left is an exothermic reaction, and the reason why is if you notice the energy of the reactants on the left-hand side is greater than the energy of the products, which means as this reaction proceeds, energy is going to be released. It's going to be lost. A couple of other important features of this graph, if you notice when you start with the reactants, there's a little hill that you have to get up over in order to reach the products. That hill is called the activation energy. All right, so the larger the activation energy, the slower the reaction is going to be. And then also, the difference in energy between the reactants and the products, that is your enthalpy change, or your energy change. If you look at the graph on the right-hand side, that is an endothermic reaction. And the reason why it's endothermic is because if you notice, the energy of the products is greater than the energy of the reactants, which means as this reaction proceeds, energy has to be absorbed. Look at the activation energy there. It's quite a bit larger than the one on the left-hand side. And then if you notice the difference in energy between the reactants and the products, that is your energy that is being absorbed. Now, if you want the reverse reaction to occur, if you want to go from products to reactants, which we will study in this class, if you notice, the energy of the reverse activation energy is simply the smaller hill that you have to get up over to go from your products back to your reactants. So if I ask for a measure of that, if you actually notice, a measure of that hill would be the activation energy minus the energy that's absorbed. That is your reverse activation energy. Okay? And so just to remind you, if the activation energy is large, okay, then that means that the rate is going to be slow. So the rate of reaction depends on how big the activation energy is. So the first type of reaction we're going to look at two in this video. The first type is going to be our combustion reactions. But in order to write out reactions, we need to make sure we're clear about diatomic elements. All right, so diatomic elements are a list of 7 elements that by themselves, they cannot exist by themselves. So instead, they exist as molecules. So there are 2 of them bound together. And these will sound familiar to you from first year chemistry. You've got H2, N2, O2, F2, Cl2, Br2, and I2. So if you ever have these elements by themselves, you need to make sure that they are diatomic. So let's look at the first type of reaction, which is combustion. So the general format for a combustion reaction is a hydrocarbon. It reacts with oxygen, and it's going to produce always carbon dioxide and water. So these are really easy reactions to predict. So for example, if I gave you ethane, and I told you it burned in air, that's a combustion reaction. So that's the formula for ethane. It's going to react with oxygen. Remember, oxygen is O2 because it's diatomic, and it's going to produce carbon dioxide and water. So all I have to do for this reaction is now balance. So I've got 2 carbons on my reactant side, so I'm going to put a 2 in front of carbon dioxide. I've got 6 hydrogens on my reactant side, so I'm going to put a 3 in front of H2O. And then if you notice, I've now got 4 oxygens from carbon dioxide. I've got 3 oxygens from water, which means it's 7 oxygens that I need. So I'm going to put 7 over 2 in front of O2. Now, I can't leave it like that. So now I've got to take this entire reaction and I'm going to multiply by 2. So it's a 2 in front of C2H6. That becomes a 7. That becomes a 4. And that becomes a 6. And I am now completely balanced. So the next type of reaction is going to be single replacement reactions that we're looking at. Now, in order to understand single replacement reactions, we need to understand oxidation numbers. So we're going to take a second, we're going to pause from different types of reactions, and I'm going to explain oxidation numbers. So let's really quickly just start with some definitions. What exactly is reduction? What is oxidation? Reduction is the gain of electrons, while oxidation is the loss of electrons. And a very easy way of memorizing that is by simply saying oil rig. Oxidation is loss, reduction is gain. And so if you think about it, we're talking about electrons. If an element is oxidized, meaning it loses electrons, its charge is going to become more positive. If an element is reduced, meaning it gains electrons, that means its charge is going to be more negative. So let's look at some rules with regards to assigning oxidation numbers. Now, oxidation numbers are simply a way of keeping track of how many electrons are gained, how many electrons are lost, and by whom. So, in order to understand oxidation reduction reactions, we have to be able to assign these oxidation numbers. So, to start off with, elements always have an oxidation number of 0. If they have no charge and they're by themselves, they have a 0 oxidation number. The sum of the oxidation numbers of compounds is also going to be 0. And then if you have a polyatomic ion, the sum of its oxidation numbers is simply going to be the sum of the charge of that polyatomic ion. Now, oxygen normally has a -2 oxidation number, except when it acts as a peroxide, O2. In that case, it has a -1 oxidation number. Now, hydrogen has a +1 oxidation number, except when it's bound to a metal, like, for example, in the example of sodium hydride that we saw before. In that case, because sodium has a +1 oxidation number, which we'll get to in 1 second, hydrogen, the hydride ion, would have a -1 oxidation number. Fluorine is always -1, and while halogens tend to have an oxidation number of -1, they can actually have variable oxidation states. Group 1 metals always have a +1, and group 2 metals always have a +2 oxidation number. And positive charge generally comes before the negative charge. So keeping all of this in mind, if you see oxygen, normally -2 for the most part. Hydrogen normally +1 unless it's a hydride. Fluorine always -1. Other halogens you can't 100% of the time tell, but they tend to be -1. Group 1 metals +1, group 2 metals +2 oxidation number. So let's look at in practice too. I've got potassium permanganate here. The first thing I look at always is oxygen. Oxygen is always -2 unless it's a peroxide. And potassium next because it's always +1. So now I need to determine the oxidation number of manganese. Well, that entire compound needs an oxidation number of 0 overall. Well, oxygen is -2, but there are 4 of them, so that's a total of -8. Potassium has a +1, so in order for the overall oxidation number to be 0, manganese must have a +7 oxidation number. Okay. For the next one, oxygen is always -2 again, and if you look at that, that means that the total oxidation number contributed by oxygen is -8. Well, here's a problem. This is a polyatomic ion with a 2- charge, meaning the overall oxidation number needs to be -2, which means since oxygen is overall -8, sulfur must be +6 in order to have an oxidation number of -2 for the entire polyatomic ion. So we're now going to be able to talk about single replacement reactions and really analyze them. So the general format for a single replacement reaction is one element, A, reacting with a compound, BC, and A actually goes in and kicks B out, and it'll become AC plus B. So let's look at an example. Notice here, it's asking me to write the net ionic equation and to identify what's being oxidized and reduced. So when I start out, I have solid magnesium, which means I just have Mg, and it's going to react with copper 2 sulfate, which would be CuSO4. Now, magnesium, a positive always kicks out a positive, a negative kicks out a negative. So magnesium, the only thing it can kick out is copper. So magnesium kicks out copper to form a compound with sulfate, so it would be MgSO4, and then copper is now by itself. Notice magnesium on the reactant side and copper on the product side do not have a charge, and that is key here. This is why it's an oxidation-reduction reaction. If instead of magnesium I had fluorine, for example, F2, F would have kicked out SO4 because those are both negatively charged when they're ions. So now I need to write the full ionic reaction for this. Well, I start off, I have magnesium. Copper sulfate is soluble, so I'm going to have copper ions and sulfate ions. Magnesium sulfate is also soluble, so I'm going to have magnesium ions and sulfate ions. And then I have copper there. Remember, I need to eliminate the spectator ions, so I'm going to eliminate sulfate. That's the only thing that is a spectator. Because notice, magnesium on the reactant side is an atom, while it's an ion on the product side. And so what I end up with for my net ionic equation is Mg reacts with copper ion to produce magnesium ion and copper. So now this is the reaction that's happening. This is why it's called an oxidation-reduction reaction. Because if you notice, magnesium is losing electrons to become Mg2+, which means magnesium is oxidized. Copper goes from a +2 to a 0 charge, which means it gained electrons, which means it is being reduced.